Okay, today we're gonna cover the resistance topic. Let me go back to the resistance. Here you go. So today we're gonna cover the series and parallel resistance, right? So few things I wanna show you in these slides, and these 3 slides are the questions on the U word. Okay, so we pay attention to what this one. So this was what I was talking yesterday. I got this picture. So I thought this is a better time I should show you. So what this picture is showing you, this is how the, as I told you, arteriolar dilation, right? That means small this picture. Yeah, there you go. So this is the organization of the systemic vessels. So how the vessels are organized. So you have aorta, then you have arteries, then you have arterioles, where we apply the dilator and constrictor in yesterday topic in the cardiac venous loop curves, right? Cardiac loop curves. So cardiac function curves, sorry. Arterioles, then we have capillaries, then venules, veins, and vena cava, right? This is how the systemic presentation of the vessels is look like. Now, this is there showing you the pressures in different vessels, right? You have aorta, arteries, arterioles, capillaries, venules, veins, vena cava, right heart. This is the same presentation. On the x-axis, on the y-axis, they are showing you about the pressure. So can you tell me anyone in which of these vessels there is the greatest drop of the pressure and why? You see this picture? Can anyone tell me? Because when you try to tell, it is better for you guys to understand. So in these arteries, as I showing you, this is the pressure 40, 80, 120. Which of the vessels have the tremendous or the greatest drop of the pressure?
Aorta?
No.
No.
Here you go. Arterioles.
Oh.
Arterioles. Very good. Why? Because you see the arteriole, aorta, you have 120, 80. Arteries, it's a little bit lower, 110 over 70. Then in arterial, you see from the 80, it dropped down to 40.
Oh, you said dropping the pressure. Oh,
Dropping
sorry.
the pressure.
Oh,
Yeah.
got it.
No,
got
no
it.
problem. I was asking about the dropping of the pressure. And this was the U-word question. So greatest drop of the pressure is in the arterioles. And then on the capillaries, this is dropping down over to the right atrium. In the right atrium, your pressure is 0. Always remember, the pressure in the right atrium is 0. And so why the pressure is lower in the arterioles? Why there is the greatest drop of the pressure in the arterioles? If you go back to this picture, you see this is the aorta. You have highest pressure. Then in the arteries, a little bit highest pressure, not low. According to this picture I show you. If it is 120 by 80, this would be 110 over 70, like this. But over here, when it is branched into the arteriole, you see many branches from the arteries. So there is the pressure is basically distributed. So blood is coming from here, here, here. Let's say the pressure is over here 110 over 70, then it is distributed over here. So there will be a tremendous drop of the pressure in the arterioles. The reason is due to the branching network of the arterioles. So this is your word question. They will ask you why pressure is. Okay, somebody raised the hand. So what's the question? If you have
Hello. I have a question. You just mentioned that the pressure is distributing over here, right? And that's the reason for pressure dropping in arterioles, right?
Yeah.
But aren't these arterioles and arteries are in parallel connection and in like in +2 in high school we studied that in parallel connections, the pressure, the voltage difference remains the same for each connection.
I didn't.
So shouldn't be. I'm saying because these arterioles are in parallel connection to the arteries and the aorta and the heart, right? So shouldn't all of them be getting the same pressure?
The arterioles are connecting in the parallel?
Yep. You have a parallel connection, right? Like from one source, you like the parallel connection, right?
Arterioles are within the organ or outside of the organ? These arterioles are within the organ, right?
Yeah.
So arterioles within the organ, they have series connection. This is what I know about this parallel and the series resistance. That the series resistance or these connections are in series within the organ, and between the organ, they are in parallel connection.
Okay.
Right over here, I'm just talking about the pressure drop, not the resistance, right?
Okay,
So
okay.
pressure drop is basically why, because there is like a branching, a tremendous branching patterns of the arterioles, which leads to the drop of the pressure. That's why the U word will be asked you that similar picture they will showing you like this, not this way. They will show you just a line and then they will ask you what you see in at which points there is a dropping of the pressure. So you have to choose the arterioles. The second things they will ask you about the cross-sectional area. Now you can tell me which one having the highest cross-sectional area. This is second U word question.
Capillaries.
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 Yeah. So basically one cross-section area is, let's say this is your aorta. So this is the one cross-section area of the aorta, because most of the people select aorta that this is talking about the cross-section type of thing. Aorta must having the highest cross-section area. No, the aorta have the least lowest cross-section area, as you can see over here. Capillaries have the highest cross-sectional area because you have to sum up all the capillaries. All the capillaries have an individual cross-sectional area. And when you sum up all the cross-sectional area, you will come to know that the capillaries have highest cross-sectional areas. Over here, if you can see, let me go back to my picture. This one again, these are your capillaries. So cross-sectional area, if you sum up the every capillaries, the cross-sectional area would be greater than the aorta. Aorta have only one vessel, so cross-sectional area will be down. Then the next question, the U word will be, this is the second question. One, I told you about the pressure. The second, I told you about the cross-sectional area. The third question, they will ask you about the velocity. So what is the velocity with the cross-sectional area? So velocity is inversely proportional to the cross-sectional area. Velocity is inversely proportional to the cross-sectional area. So if you have increased cross-sectional area, the velocity would be decreased. And if you have decreased cross-sectional area, your velocity will be increased. So highest velocity of the blood is in the aorta, not in the capillaries. Then that is another question of the U word. Then I will come towards this hemodynamics, in which I will particularly this is the today topic in which we will discuss about this Poiseuille equation, what is there showing hemodynamics. So Poiseuille is basically showing you the relationship of the your blood flow, the pressure and the resistance. So he built up this equation in which he said that the flow is equal to the pressure gradient divided by the resistance. So Q is the flow, P1 is the upstream pressure, that is at the start of the vessels, P2 is the pressure at the end of the circuit of the vessels, and R is the resistance in between these pressure, which is within the vessels, right? So this Poiseuille is basically showing you, this is very important equation. You can write down this in either way. Let me show you the screen. That Q is equal to delta P over R, right? And you can like calculate the resistance by this way, that is delta P over Q, right? This is how you can calculate the resistance also. But then he make this equation more expanded, but I will let you know about that later on. First, you have to understand that the flow is proportional to the directly proportional to the pressure gradient and inversely proportional to the resistance. So what is inversely proportional to the resistance is Q. Q is your flow. So Q is inversely proportional to the resistance. So if you have higher resistance, your flow will be decreased. And if you have decreased resistance, your flow will be increased. This point you keep in mind. This Poiseuille equation is very, very high yield. Few equations which I told you, you have to keep in mind. Among those, this is another equation which you keep in your mind. Going to in detail in the next few slides. So this is Poiseuille equation applied to a single vessel. This is the P1 pressure gradient. Sorry, P1, P2 is the pressure gradient. This is the P1 at the upstream, and this is the low stream. The resistance is in between the P1 and the P2, which is within the vessels, and this is there from the flow of the blood, right? Now, the determinants of the resistance. So how you can determine the resistance? So as I told you, if you rearrange this equation, Q is equal to delta P over R. So I move R over here. So I say resistance is equal to delta P over Q, right? So what is the Q? This one, what you can say determinants are you're writing what that called milliliter per minute. This is for the Q you're using, and these 1 mm of Hg you're using for the pressure. So this is how you can write down the units of the pressure. That is mm of Hg per milliliter per minute, right? So these are there, that's showing you the units of the resistance. So now they will also tell you that the resistance of the vessel is also determined by the three major major variables. So resistance is itself dependent upon V, which is viscosity, L is for the length, and R is the fourth power of the radius, right? Which is your vessel radius, right? And radius is very important in determining the resistance of a vessel. So if a vessel have low resistance, so lower radius, what would be the effect on the resistance? Increase or decrease?
Increase.
Increase, right? Because it is inversely proportional to. Now you have to exclude all these, that R is your resistance. So this is saying it is directly proportional to VL divided by R4. V is your viscosity, L is the length of the vessels, and R is the radius of the vessel. So R is in turn in other ways, R is directly proportional to the viscosity. Resistance is directly proportional to the length of the vessels, but resistance is inversely proportional to the radius of the vessel, which is fourth power of the radius, right? This is how you can write down. So what the Poiseuille will do, or what is the final equation when you put these all together. So let me show you the next slide. I didn't make a slides because it is very easy to explain over here. So Q is equal to delta P over R. So I know that R is equal to VL over R4, which I told you R is directly proportional to the viscosity, R is directly related to the length, and inversely related to the radius. Now you tell me, what is viscosity?
Thickness?
Thickness of the blood, right?
Yes.
Can you give me any example in which the thickness of the blood is increased?
Polycythemia.
Polycythemia, yeah.
Yeah, very good. In polycythemia, your viscosity will be increased, right? So if your viscosity will be increased, so what will be the effect on the resistance?
Resistance will be same.
Increase, right? Because
Increase,
they're
yeah,
directly proportional, right? So over here, if I increase the resistance in case of viscosity. In case of polycythemia, if I increase the viscosity of the blood, I increase the resistance. Now, can you tell me any other example in which you have the decreased viscosity? Why I'm asking you, these are the U-word questions.
Anemia.
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 So in anemia, you have decreased viscosity. So what would be the effect of the resistance?
Resistance will be up, increased. No, sorry, decreased.
Decrease, because viscosity is decreased in anemia, so resistance will be decreased also,
Yes.
right? And the radius I told you, which you need to understand in your own words, right? So this is the Poiseuille equation in which you have to relate the flow with the radius, pressure, length, and all that. This is a very important equation, the overall equation, which is, let me see if I have taken the slide of that equation. I forgot to take that one. No, right over here. Yeah, the next slide. So what he did over here, so Q is equal to delta P over R. So we know that the R is equal to VL divided by R4. So this is the final equation, which I'm telling you is the important equation that you have to remember, because by this way, you can answer to the question, right? You can answer to the question. In this question, you are doing what? R is equal to VL divided by R4. So you are reshifting the things. VL is coming down and R is going to up and multiply with the pressure. So now flow is dependent on the pressure, the radius, and inversely proportional to the viscosity and the length. Now, if the viscosity is increased, what would be happen on the flow?
Decreases.
Decreases, you see, because they are inversely proportional. I increase the viscosity of the blood by giving you a polycythemia example. If viscosity will be increased, the flow will be decreased, but the resistance of the vessel will be increased, which I told you in this way, right? Viscosity is directly related to the resistance. These three equations, like Q is equal to delta P over R and R is equal to VL divided by R4, and this final equation, they are very important to answer many questions in the U-word, particularly because I don't know about the real deal. I didn't give the exam yet. Okay, so this equation is very, very important. Now coming to the next thing, which is just you need to know, right? Because they can ask you. That is the concept of the resistance. So they will ask you, the flow of the blood is actually in the way of laminar flow and turbulent flow, right? So now this picture is clearing you about the how the laminar flow is look like in the vessel and how the turbulent flow will be look like inside the vessel. So you tell me where the actually you found the resistance. Resistance is where happen inside the vessels, in the center or at the periphery. This is common sense.
Periphery?
Periphery, in the vessel's blind, right? Let's say this is your vessels. So you will feel the highest resistance on the periphery over here. That's showing you that the arrows are a little bit slow. Why? Because there are the highest resistance. You are passing along a subsurface, right? So you are facing the resistance. So where the resistance is the least, that is at the center of the blood. You see, in the center, the blood flow is very fast, right? So that is one thing you have to keep in mind, because they can ask you, where is the least resistance inside the vessel? So the least resistance is inside the center of the vessel, whereas at the periphery, the resistance is increased, right? This is another question they ask you. In case of turbulent flow, it is non-layered like this type of thing, and it is more possible for the creating the murmurs and all those of the brood sound which you hear. Turbulent flow of the blood. So, and this was the only thing I want to share over here. And there is one more thing which Kaplan is saying, maybe ask in the question, that you have to just remember. So what is that in the next slide? That is the Reynolds number. It's not giving in the first stage. So Reynolds number, the equation is like this: diameter, velocity into density by the viscosity. So you just have to remember that if viscosity is down, in case of Reynolds number, they give you a like variety of form of the equation, but viscosity always be down, because you can remember in case of like a equation way or a mnemonic way, that's viscosity is density increased, and so it will lie below this line, like in any equation. If you put the equation and you cannot memorize like diameter, velocity, density, who come down this line. I'm talking about the equation. If they ask you to tell us about the Reynolds number, what is the correct equation? So where the viscosity is down, you have to probably correct that option. This is also Kaplan is saying. I don't know they will test it or no. So in Reynolds number, you have to just memorize these two numbers. These are the units. In case of turbulent flow, the Reynolds number is greater than 2000 units. In case of laminar flow, it is less than 2000. So they can give you a question scenario, whatever, and then at the end of the question, they can ask you that how can you recognize that this is the turbulent flow of the blood or the laminar flow of the blood, depending upon the Reynolds number. So you have to pick the option. If it is greater than 2000, it would be turbulent flow. If it is less than 2000, this is the laminar flow. This is an extra point, might be tested in the legal deal or the U-word. I haven't recalled that this is tested in the U-word, but Kaplan is saying you should keep this point in mind on the safer side, right? So I will go with this equation on the parallel and the series, right? Whatever I have understand, honestly with you guys, I will teach you. Extra point, if you have in your mind, you can inbox me or ask me after the session. I will try to answer those questions. So this is the equation basically we apply on the resistance, because in case of series and parallel resistance, you're gonna study about the resistance when it is in the series manner and the resistance when it is in the parallel circuit, right? These are the two circuits. So what they are showing, this is they are showing you about the series versus parallel circuits, right? So over there, this diagram is typically showing you about the series circuit of the resistance. So basically what you need to know that the resistance in the system, let me start from here. So resistance in the system, or you can say resistance in the circuit, is of two types: series and parallel, right? So then we will slowly discover what is resistance. When we slowly discuss about what are the series pattern of resistance and how the parallel resistance will happen in your body. So again, we will apply the same things on the formula. So as we know that the resistance is this, let me wipe it off so it won't overlap so you clearly see. I make every slide before coming over here, so I will go over that slides and we will read from there to save the time. So this formula again I write for again repetition that flow is directly proportional to the pressure gradient over the resistance, and resistance in your body or the resistance in the circuit is in two ways: series pattern and the parallel pattern. These are the two patterns of the resistance. Now series pattern, you have to remember 4-5 points which are very important for the series and the parallel. There are some rules or the points which you have to remember or which you have to learn by heart, because these are very important to answer your questions. So first point is, which you have to remember, that the Q, which is your flow. So flow is equal at all points, and I will tell you how. So in case of series resistance, or you can say when the resistance is in the series pattern, then the flow is equal at all points, right? That is one. Second point is that the total resistance is equal to sum of the individual resistance. So if you are sum of all the resistance, like resistance 1, 2, 3, I will make the slide soon. So when you added every resistance of the 1, 2, 3, then you will get the total, and the total resistance is always equal to the sum of the individual resistance. Third point, you have to remember that the total resistance is greater than the individual resistance. That point is very important, because in the parallel resistance pattern, or in case of resistance in parallel pattern, the total resistance is less than the individual resistance, which I will prove in next slides. So what we learned, that the total resistance is equal to the sum of the individual resistance, then total resistance in the series pattern is greater than the individual resistance. The fourth point, which is I also explained at the end of the session, that adding resistor or adding a resistance to a system in series will increase the total resistance of the system. This will all you have to learn, that if you add a resistance to the system in case of series, the total resistance of the system will be increased. These are the fourth point. Fifth point, I will explain together with the parallel system, but 4 points you have to remember. So what are those? That the flow is equal at all points. Second is that the total resistance is equal to the sum of the individual resistance. The third point is that the total resistance is greater than the individual resistance. And fourth, if you add any resistor or the resistance to the series pattern, the total resistance will be increased. So this is how the resistance in series. So how the resistances look like, this is the picture. So this is a total resistance. You have first resistance. Resistance is just like a bump. You know, the bump which are like a speed breaker. It is just like that. You can like keep in your brain like a speed breaker type of a thing on the road. So total resistance is equal to R1, R2, R3. This is how it is graphically, or you can say picture, I can demonstrate it this way, right? So now what I say, in case of series, RT is equal to R1, R2, R3, right? So I give them a value. R is 1. So R1 having 1 resistance, R2 having 2 resistance, and R3 having 3 resistance. So simple math, when you added all these numbers, you will get 6. So what you concluded, that the total resistance is equal to the sum of all the resistance. And the second point, if you tell me that the total resistance is 6, is it greater than resistance 1 or no? RT is 6, R1 is 1. So RT is greater than R1 resistance or no?
Yes.
Yes. So this
Yes.
is my other point, that the total resistance is greater than the individual resistance in the series pattern, right? In the series pattern. So that is my second point. So I explained you about now the flow, first point. So how the flow is equal at all points, because let's say this is the vessel and you are having the speed bumps. Let me tell you this way. You see, these are the vessels they're saying you, like this is one bump, this is second bump, third bump, right? Now you tell you these are the resistance. So this is the flow, right? Flow is what, when you are flowing a blood, electricity or anything which is flowing in a circuit, they are telling you about this one. So flow, it is coming over here. It is same over here. It is same over here. So this you have to remember, that in case of series pattern, the resistance is equal at all points. All points of the resistance are all points in the vessel wall, right? Sorry about that. Let me wipe it off because it's covered the next slide. So in case of series resistance, flow is equal at all points. That is first point I explained you. Second point I told you that resistance, total resistance in case of series is equal to the sum of the individual resistance. And the third point I explained you that the total resistance in case of series is greater than the individual resistance. About the fourth point, I will come to end up when we study about the parallel resistance, right? So this is the story about the series resistance. Let me read from here also. So what they're saying, total resistance is the sum of the individual resistance. RT is equal to R1, 2, and 3. Then I tell you the total resistance is always greater than the individual resistance. Then adding a resistor in the series will increase the high resistance. Connecting the resistors in a series result in high resistance of the system. The same thing they are talking you about over here in this slide. Now go toward the parallel system. So what are the points in the parallel system? I come this slide later on. So in case of parallel resistance, first thing you have to remember that the parallel resistance will take in the reciprocal, right? This is normal. We are taking the parallel thing in case of reciprocal form, in the mathematical form. This you have to remember. Now, what is the differences in the parallel and the series? So in case of parallel resistance, the Q, that is flow, is not equal at all points. And I will show you in the picture why not, right? So we said in the series resistance that flow is equal to all points. In case of parallel resistance, I'm saying flow is not equal at all points, right? First point. Second point is, in case of series, I told you that the total resistance is equal to the sum of the individual resistance, which I show you by adding all the resistance. That is my second point in case of series. In case of parallel, reciprocal of the parallel resistance, as I told you that the resistance in the parallel system is taken in the reciprocal, 1 over R1, 1 over R2, or 1 over R2, which is the total resistance. So they are explaining that the reciprocal of the parallel resistance is sum of the reciprocal of the individual resistance. That is the same point. Just you have to add the word reciprocal. This is the same as I said in the series that the total resistance is equal to the sum of the individual resistance. In parallel, reciprocal of the parallel resistance, reciprocal of the total parallel resistance is equal to the sum of the individual parallel resistance. That is the second point. Now the third point, sorry, I put the fourth over here, third on the right because I forgot this one. So third because of matching, so you can understand. In case of parallel resistance, the total resistance is less than the individual resistance. I didn't put it 1 over RT. I will show you in a minute why I didn't put that. But in case of parallel system, the RT, that is the total resistance in parallel system, is less than the individual resistance in the parallel pattern. That is different from your series. You see over here, in case of series system, the total resistance is greater than individual resistance. And I told you over here why it is increased. Now, in case of parallel resistance, I told you that the total resistance in parallel system is less than the individual resistance. So in parallel, the total resistance is less than the individual resistance. And in case of series, the total resistance is greater than the individual resistance. Now, how the parallel resistance is, and the fourth point, let me complete this one. Adding of a resistance in a parallel circuit will lower the total resistance. That is the difference. However, in case of series pattern, if you adding the resistance to the system, the total resistance will be increased. This is very important because I apply this fourth point in a question manner, which might be you what will be asking you this question, right? So in case of series, if you add a resistance, your total resistance will be increased. In case of parallel resistance, if you add a resistance to this parallel circuit, the total resistance will be decreased, right? Now, how the parallel resistance is presented. As I told you, this series resistance is presented by this way, right? So parallel resistance is 1 over RT is equal to, this is how it is in parallel. You know, series is like you are parking the car in a series on the road, one after the other, right? So in parallel, you are parking the car parallel to each other as you are parking in the parking lot. So that is how the best example of the parallel resistance. 1 over R1, 1 over R2, 1 over R3, right? So I give them the values also. Value of the R1 is 1, 2, and 3. The similar I give over here for the resistance in the series circuit. The only difference is this is added by 1 over R1, 1 over R2, 1 over R3, right? Now I did some calculation on the parallel resistance. So what I did, I added 1 over RT is equal to 1 over R1, R2, 1 over R3, right? So then I added the number, right? I leave this because we have to take in the fraction of this one. It could be some value like a 6, and then you are adding this number, the final value. You can do it yourself. This is just a math. That's why I'm not wasting time on that. But you will get a value of 11 over 6. So basically, you take the fraction of these three values. You know the fraction in the maths or no? So fraction कैसे लेते थे? You put over here 1, 2, 3. Whereas I remember my math is very poor too. Okay. So I take 1 here, 2, 1 over 2 and 3. Then I will take 3, 1, 1, 3. So then I multiply 2 by 3 is equal to 6. Then I multiply 1 into 6, 6, 1 over 6, 6. And this is how you will do this math. 6, 7, 8, 9, 10, 11. You remember this or no? Then you are multiplying and adding them. If you don't remember, then do it yourself, okay? But the bottom line, you have to take the fraction of the bottom, which is denominator, and then multiplying with the nominator and do, but the bottom line, you will get the value of 11 over 6. If you don't understand, then I will do this math on the next session, okay? Then let me know, okay? So 11 over 6 is the resistance will be you get in case of the parallel circuit, right? So what you need to do, you are concluding that the parallel resistance 1 over RT is equal to 1 over R6. Then I will do what? I will shift it. I will put RT like as over here. Let me go back. This is 1 over RT is equal to 1 over RT is equal to 11 over 6. Then I do what? RT over 1. I rotate the equation. So it becomes 6 over 11. I put this up, 11 down like this, rotate the equation. RT go up and 1 coming down. This you know, it is pretty simple. I don't think so any one of you don't understand what I'm saying over here, okay? So they have like shifted the equation, round the equation, right? So when they rounded the equation, my result is this much. RT is 6 over 11. 6 over 11. So if you put the 6 inside the like divided 6 by 11, the value which is coming, it would be less than 1. I didn't count this one, but you can do it yourself. You will be concluded that this value is less than 1. So what will be my conclusion? That RT in peripheral resistance is equal to 6 by 11. I concluded. So that value is less than the individual resistance, right? That value is less than the individual resistance. What is the individual resistance in case of the parallel series? 1 over RT is 1, right? However, if you put the 6 inside and divide it with the 11, it will become 0.0032 something, right? You can do it on the calculator. So what you will be concluded that this total RT resistance, which is 6 over 11, or in points value, it is less than the 1, which is R1, or it is less than 2 or 3 value. So that is my conclusion that in parallel circuit, the RT value is less than the individual resistance, right? Total resistance in parallel circuit is less than the individual resistance in the parallel circuit, which is opposite to the series circuit in which you say that my total resistance is greater than the individual resistance. How? Because my total is 6 and the individual resistance 1, 2, 3, it is greater than the individual resistance. So that is how you will conclude these kinds of resistance and your values over here. Now let me go back to this point, leave this one. So they're saying the same thing. When resistors are connected in parallel, the reciprocal of the total resistance is sum of the reciprocal of the individual resistance. They do this one. Now they're saying connecting resistors in the parallel circuit result in low resistance system. Total resistance is always less than any individual resistance, which I concluded with you, and you know that. And the fourth point, we're adding a resistance in parallel, lower the resistance of the system, right? Which is opposite to the series, in which when adding a resistance, connecting a resistance in series will result in higher resistance of the system, right? So that is the story about series and the parallel resistance, right? Now the fifth last point. I told you about the 4 points in parallel and the last point which I told you about the flow. Now the flow is what? So if the flowing is through this vessels, the flow will be go over here, then flow will go over here, and then flow will go over here. So flow will be divided, isn't it? Now flow is not parallel, not in a series. Let's say flow is coming over here, then some is going over here, some is going straight, and some is going down, right? So flow in the parallel circuits is not equal. That is the reason. If you see the picture, then you can understand why flow is not equal in parallel circuit, right? That is the first point. Second point, what I told you, let me go back. Second point, reciprocal of the peripheral resistance is sum of the individual resistance, which I do over here. I put the 1 over RT and added them together and get the value that it is equal to the sum of the individual resistance. And the last point which I added over here is RT is less than RI. That is total resistance is less than the individual resistance. This is I concluded in this phase 6 over 11, which is points value, and it is less than the individual resistance. If you see your individual resistance in R1 is 1, which is greater than the points coming over here, RT, which is 6 divided by 11. You do in a calculator, you get the value, right? Now the fourth point, which I will come with the question, and you will tell me this one. I'm sure you will able to answer me now. So now the fifth point. So fifth point is basically telling you that I'm telling you for this scenario, parallel resistance, series resistance, this and that, in parallel, flow is this, fly is this. So you're thinking why we should know about this one. What is the importance of knowing the series and the parallel circuit? Because in our bodies, these are circuits are present. So in our body, we have the series and parallel circuits. So by series resistance, where it is present, series resistance is present inside the organ. As I'm telling you that the fifth point is series resistance is intra-organ. Within the organ, the resistance is in series pattern, right? So if you think about what you will be play with you, they will tell you a question scenario and they will tell you about any one organ, let's say liver, and they will talk about this one and they will not say the word series. They will ask you guys, you should know that they're talking about the liver, right? So they will talking about the liver, then you have to conclude it that they must be asking me something about the series. So might be they're asking that what would be the flow in the liver? So then you have to think the series resistance in the liver. What would be the effect on the flow? The flow is equal at all points. So you will choose that option in which it is written that the flow will be same in all the points in case of the series resistance, right? So these kinds of questions. So series resistance is intra-organ, that is within the organ, while the parallel resistance, which is most important, it is present between the organs. Now, as I told you, in your mind, how you can remember, let's say this is your, I give you the example of your liver, right? So inside the liver, if there is a flow, blood vessels and all that, so resistance inside the organ is present in the series, right? And resistance between the organ is present in the parallel, or you can say the resistance between one organ and the other organ, organs are present in the parallel resistance way in the circuit type of equation, right? Circuit type of thing. So how you can graphically present this way? What is I'm telling, repeating again, series resistance is inside the organ, parallel resistance is in between the organ, that is between the heart and the GIT and the kidney and the lower. This is how the parallel resistance happen. So the better picture to understand this series and the parallel resistance is, let me go back to the next slide. This is the graphical presentation of the series and the parallel circuit. But the parallel circuit is very important. Most of the question, I believe, so they will ask you about the parallel circuit or the parallel resistance, because you can see this is your liver, this is your stomach. So now they are, you see, they are connecting in the parallel, right? Parallel flow is coming and this is divided in this way, right? So they are showing you liver, this is your stomach, pancreas, intestine, endocrine glands, kidney, and this is your muscles and the bones. So this is how the organs are within your body are happening in the parallel circuit. So these are the 4 or 5 points about every system which you need to understand over here. I will finishing this one and then go back to the first aid and read, which I don't think so. You need to read that one because I told you about every specific important point. I will get back to this equation that how resistance is now happening in the series and parallel pattern. So what is now the bottom line? I'm putting a question. The question is that if a woman is donating an organ, right? So when woman is donating a kidney, this is my question. So you have to tell me what would be the effect on the flow, on the resistance, on the cardiac output, and on the heart. Can you answer now or no? So first thing is the woman donate the kidney, right? So we will think about the parallel resistance, right?
Yes.
Because kidney is in the parallel, right? You have, let's say, above you have the GIT, below you have the kidney in the middle, and down you have the muscles and all that, right? So when you are donating a kidney, the woman is removing the organ from the body, isn't it?
Yes.
So when she removes the organ from the body, she is basically subtracting the organ, or she's subtracting the resistance, right? Let's say, let me do like this one, maybe this is better, you guys understand. So let's say, paint the color. So let's say this is parallel circuit, right? And this one is the flow, right? So this is your GIT. This is your kidney. And this is your muscle, let's say, right? Muscle. So now this woman have donate the kidney. So kidney is get out of the body. So she removed one organ from her body. So what would be the effect if you are removing an organ? If you adding a resistor to the system in case of parallel system, what would be the effect on the total resistance? It will be decreased.
Yes, it will be decreased.
Let me go back to that slide. So you might say what Noni is saying. She didn't explain us this point. So this is parallel resistance. So I told you adding resistance in parallel circuit will lower the total resistance, lower, right? But in this case, we are removing the organ, right? So we are subtracting the resistance, not adding. So if I'm removing an organ, if adding an organ or adding a resistance will lower the total resistance in case of parallel circuit. If I remove the organ, it will go opposite. It will increase the total resistance in a parallel circuit. Isn't it?
Yes, right? Yes, right.
I remove the kidney, right? I remove the kidney. So what would be the effect on the total resistance in parallel circuit? So we will go opposite to that one. When I'm saying adding a resistance to the parallel circuit with lower the total resistance. So now I'm removing a resistance. So when you are removing a resistance, you will go opposite way. If you're removing a resistance in a parallel circuit, it will lead to the increased resistance, right? So up to here, you can answer, right?
Yes.
You wipe it off because it comes to the other slide. So you are saying that when you are removing kidney from the body, it will lead to the increased resistance in a parallel circuit, right? So let's write about it.
Yeah.
So what I'm saying, sorry about that. I'm saying my resistance increase in case of parallel resistance, right? In case of parallel, when I'm subtracting the kidney or subtracting the organ will lead to the increased resistance in case of parallel circuit. Now I have to go with the equation. So what is my favorite equation? It is Q flow is directly proportional to delta P over R, right? Or you can say we are not related to the pressure over here. We are talking about flow and the resistance. So I can say flow is inversely proportional to the resistance. Isn't it?
Yes.
You keep this picture in your mind?
Yes.
All of you are 7, okay? This is very 8 people, okay? Pay attention. So I told you this much, that the Q is, flow is inversely related to the resistance because you need to answer me. Now I'm making a graph over here and you will answer me. Let me make it. So what is the graph you have to choose? So this is how the U word will be played with you. So R is resistance, Q is your flow, cardiac output, and your heart rate, right? So question is the same. So I give you A, B, C options. So A option, I'm just giving you value. You just put in attention and you will answer me what is the correct value. Okay, correct answer, okay? And you can do that, I know. Okay, you see this thing? So now what I told you, you have to answer. I told you then when a woman donates the kidney, she had removed the organ from the parallel circuit. So we concluded when she donated the kidney, her resistance is increased because adding a resistance to a parallel circuit lower the total resistance. But removing the resistance from a parallel circuit will increase the resistance. So I concluded that Q is directly proportional to delta P over R. And now I have to say Q is inversely proportional to R. And then I concluded that R is increased. Now tell me all this. So what would be the effect? Which one is the correct option? I'm giving you time. So if you answer this much, you are good to go. I told you all that. So which option you will pick? A, B, or C?
So, I thought C.
Sohani?
Yeah, sorry.
Sohani?
Yes.
Okay, good. Anyone else want to answer? No?
How do we differentiate between A and C? Both options resistance is
A is the option. I'm giving just options. I make it my own self.
yeah,
I
okay.
put A and B and C. I put my one correct option. You just have to correct those one.
Yeah. Resistance is
Sorry, Bob. Sorry to interrupt. I'm not explaining you what is A, what is B, what is C. Okay.
got it. Right. Yeah.
Just this is a quiz. You have to choose the correct option.
Hmm. So resistance is increased in flow, decreased in even in A, right? So, so flow is decreased, so cardiac output will be decreased as well.
As well, heart rate.
So what is your option?
But if cardiac output decreases, heart rate should increase. That's my doubt.
How?
Because when the cardiac output decreases, reflects the sympathetic activity.
But this is not sympathetic activity. I'm talking about like as you are moving an organ. You just think about that. You are going in the right way. I know you are confusing the same way I'm confusing.
Yeah,
So
C. I'll go with C.
Right? So what is happening when you increase the resistance, the flow will be decreased. Two are over here, right? So this is same and this is same, right? So now you are saying when flow is decreased, what would be happening to the cardiac output? If you have seen my previous session tomorrow, I told you flow is related to the cardiac output. Flow is what? Flow is whatever flowing towards the heart, right? Whatever blood flow to the heart is your cardiac output. If you decrease the venous return, you decrease the cardiac output. If you increase the venous return, you increase the cardiac output. So what is your venous return? Venous return is actually your flow, right? So flow is directly related to your cardiac output. So if your resistance is increased, you concluded that flow is decreased. When flow is decreased, cardiac output is automatically decreased. So when cardiac output will decrease, it is dependent on two factors, stroke volume and heart rate, directly proportional. Right? So if cardiac output will be decreased, your heart rate will be decreased. So you have to think about the bradycardia. It wouldn't be tachycardia, the flash tachycardia, because it is related to your cardiac output. The body have to maintain this resistance, right?
So it is not the baroreceptor, isn't it?
It's not the baroreceptor. They are talking about the resistance.
Right.
So this is basically concept they are asking you. You are actually understanding what is happening. They're not asking about, this is the question like a reflex tachycardia will be happen and all that. But over here, they simply want you to know that what is happened to the resistance and how resistance is affecting to the cardiac output, heart rate, and other things. So patient, whenever donate the kidney, they will come with the bradycardia, right? They will come with the bradycardia. You always remember this one. They can ask you, okay? So that was the story about these things. Now I told you in the equation for when I write these points, I told you that I will explain you the fourth point, adding a resistance and all that in a question form. So this is the question which I was discussing, and this explains you the point. So most of the time they will ask you, I haven't seen, I haven't done the cardiovascular system yet. I told Sohani also. So when I did the cardiovascular system, I see if any question, I will definitely pull those questions and put in the WhatsApp group that this is what I was talking about. Okay. So that's the story all about. Over here, I told you main things that they will ask you about this one, this picture, which is called like a tremendous drop or the sudden drop, which is you see 80 from 40, 80 to 40, all of a sudden. So they will ask you greatest drop in which one the vessels. Then they ask you about the highest, lowest velocity, and you have to pick about the cross-sectional areas regarding to the vessels. This is very famous equation, this one, and the last one which I have make over here. This is very important equation you have to keep in your mind. And then turbulent flow and the Raynaud number, honestly, I didn't see, but you have to keep in mind, they can ask you. And the series and parallel, I don't recall any question because these are all mathematical questions, right? But they might ask you these things, okay? So this is the story about the parallel and the series resistance. Okay.